Okay, so today we're going to talk about something that's really interesting and is often a topic of great curiosity in mathematics, and it is called Pascal's triangle. And here it is. All right, so Pascal's triangle. We're going to discuss three things: the basic structure, so how does Pascal's triangle work, what it is, and what's the purpose of it. And we will be studying its patterns, which is what patterns can we derive from Pascal's triangle. And finally, we will be studying its applications, which is what formulas and identities can we derive from Pascal's triangle. Hey, Brayden, I like your jacket. Is that Spider-Man? All right, and before we dive in, here's a quote from the founder or creator of Pascal's triangle, Blaise Pascal. You always admire what you really don't understand, which I suppose this makes sense because if you don't understand something, you are left in mystery and admiration of it. All right, so first, basic structure. Some of you may have seen this before. So Pascal's triangle is basically a row. It's basically an increasing row of numbers. So we start with 3 ones on the top. As you can see, there's 3 ones on the top, and then you add each adjacent number together to obtain the number below them. And we keep on adding ones on either ends of the row to make it a triangle. So in case you guys don't get what I'm saying, I'm going to annotate a bit here. So we start with 3 ones, right? And for each pair of adjacent numbers, like 1 and 1, you add them together to get the number 2, right? And you put down the 1 from the left side because, as we said here, we keep on adding ones on either ends of the row to make it a triangle. And you would see that indeed 2 plus 1 is equal to 3. And this pattern is found throughout the triangle because indeed, this is the very definition in which this triangle is built upon. So if you choose any random number in Pascal's triangle, for example, 126, you would find that indeed it is the sum of 70 plus 56, right? And if you look at another random number, say 495, you would see that it is indeed the sum of 330 and 165, the number above them. So that's basically the reasoning and creation rules behind Pascal's triangle. And also notice something really interesting, which is that, it's symmetrical. What's special about this triangle with numbers? Charlotte, we're going to get to that really quick. I didn't know it was called Pascal's triangle. Great. Well, now you do. So notice how the triangle is symmetrical. It's really interesting, but it also really makes sense because since the only method of deriving further numbers down towards the triangle is adding adjacent numbers together, it makes sense that since 1 and 3 and 3 and 1 are on both sides, the numbers you get and thus the triangle you create is symmetrical about the middle line, right? It's perfectly symmetrical, which is very interesting. Okay, so now we're going to go to the second slide. It makes sense, I guess. Could the triangle be INF? Brayden, I am so confused. Brayden, what are you confused about? What is it used for? That's what we're gonna get to. Okay, so before we get to what it's used for, let's look at some other basic rules of Pascal's triangle, just so that you get to understand, like the language we use to talk about Pascal's triangle. So unlike other configurations of numbers in mathematics, Pascal's triangle actually starts with row 0. So as you can see, the first 1 is not row 1, it's row 0, right? It may seem very weird, but as we get on into the lesson, you will see a very important reason for why it's 0. Charlotte asks, why is the like sides just one? Why is the sides just one? Well, Charlotte, part of the reason is really just to keep the triangle going, right? Because if you take away these ones, then you wouldn't really have a triangle, right? And you wouldn't be able to compute and derive all these numbers. So in a way, the ones are really just there to keep the triangle a triangle. Pascal must be a master at confusing people. Could the thing go on forever? Yes. And it does go on forever. You can always keep writing new numbers under it, right? For example, if you want to keep writing numbers here, 78 plus 13, you would get a 91 below here, right? You could keep on writing it forever. So back to the basic rules of Pascal's triangle. The top row again is row 0, right? And thus the second row with 2 ones is actually called row 1, right? It's row 0, row 1, row 2, row 3, row 4. And similarly to the row rule, the first number in each row is considered the 0th number. Braden, there is indeed that number that you put. And in fact, every number that you can possibly think of is in Pascal's triangle. And we'll get to why that is the case really quick in patterns. Yes, Braden, every number that you can think of is in Pascal's triangle. So going back to this little rule here, so that means all of these ones are referred to not as the first number, guys, but as the 0th number of each row. So that means 5 would be the first number of this row, and 20 would be the third number of this row, right? It's a little weird, but you guys will see why mathematicians choose this to be this way. Asher, I mean, there isn't one that is written with alphabet yet, but I guess if you want to create one, you could create one with your own rules. I think that would be really cool. You could try it out. Braden says even pi. So Braden, sorry, that is a little confusing. So no, what I meant by all numbers is all positive integers, right? So any positive integer you can think of is on Pascal's triangle. So for example, 9999999 is on Pascal's triangle, but decimals and fractions and pi, unfortunately, isn't on Pascal's triangle, because you see, like, all of the numbers on Pascal's triangle are integers, and integers plus an integer is only an integer. So all integers can be found on Pascal's triangle. Okay, so we are done with the basic rules. And before we move on to more interesting patterns, are there any questions about the basic rules of Pascal's triangle?
Not gonna lie, I wasn't really here for the first section, so.
Okay, Asher, I'll give you a really quick recap. So basically, Charlotte, you have a lot of questions. So why is it a triangle? Why does it exist? I'll show you really quick. Let me answer Asher's question real quick. So basically, Asher, I guess this is a really quick review. Pascal's triangle is really just, you start with 3 ones on the top, and then you just keep adding adjacent numbers together to obtain the numbers below them, and you keep on going forever. Yeah, Braden, exactly. It's a triangle. The Pascal's triangle is just a shape that spreads out forever. And indeed, this shape spreads out forever, and you will notice that these numbers add up to the number below them. These 2 numbers add up to the number below them, and these 2 numbers add up to the number below them. Right, it's a really simple mathematical configuration that actually has a lot of interesting patterns.
For the
And
outline for the triangle, it's like 1, 1, 1, 1, 1, 1, 1, keep on going down. There's it keeps on going up to it gets like that. I don't know.
it keeps on going down. It is a forever increasing triangle. And again, the top row is row 0, and the first number in each row is considered the 0th number. Okay, guys, this is getting boring. Let's get to some patterns, okay? You guys have a lot of questions. Charlotte says it's not really like a triangle because it's actually like a shape made by hexagons resembling a triangle. I suppose that is a fair point. Okay, patterns. All right, guys. So Braden, this goes back to what we were talking about, why every number you can possibly, every possible integer you can think of is in Pascal's triangle.
Oh yeah, wait, because the yellow one, the 1, 2, 3, 4, 5, 6, 7, they can keep on going down, right?
Precisely. So Braden already noticed this pattern. So guys, as you can see labeled here, we know that the 0th row of Pascal's triangle is all ones, right? But the very next row is actually all of the counting numbers. In other words, all of the positive integers, right? Because it makes a lot of sense, because if you start with 1 here, you add 1 to it and you get a 2, right? And after you have the 2, you add the 1 to it and you would get the 3, right? And after you have the 3, you add 1 to it and you get the 4. And after you have the 4, you add 1 to it and you get 5. So this pattern just keeps on going. So you start with integer 1 and you keep on adding 1, which means that Pascal's triangle contains every possible positive integer that you can think of. Braden has another question. I wonder how a simple way to keep count of crops in the past becomes something so complex like this. I suppose this is indeed proof of humanity's advancement, isn't it? All right, and not only is the pattern restricted to counting numbers, there's a third pattern too. So triangular numbers can be found in the second row. Remember, guys, this is the third number in each row, but this is referred to as the second column. So if you don't really know what triangular numbers are, it's basically the sequence you get by adding consecutive integers to get to each other. So basically, the first triangular number is 1, right? The second triangular number is 1 plus 2 equals 3. The third triangular number is 1 plus 2 plus 3 equals 6. The fourth triangular number is 1 plus 2 plus 3 plus 4 equals 10. And it keeps on going forever. So you just keep on adding larger integers to it to get triangular numbers. And as you can see, these numbers are all found in column 2 of Pascal's triangle, right? 1, 3, 6, 10, 15, 21. So it's really interesting because not only can you find all of the counting numbers in Pascal's triangle, there is the second row, which contains all of the triangular numbers that exist. And that is really interesting. Charlotte says, I bet you use DuckDuckGo. No, I actually use Firefox. Do you know what Google is? Yes, I'm using that right now. Why did they start with 3.14? How was pi calculated? Well, a brief response is that pi is the ratio you would always get when you divide the circumference of a circle by its diameter. And it turns out that no matter how big the circle is, the ratio is always 3.14. If you're curious, you can search it up on Google yourself, or we could talk about this in another class.
Could there be a square or like rectangle version where it goes down like this one?
I think that would be pretty difficult to construct because as you go down more and more, the number of numbers increase, right? So I think a Pascal's rectangle would be hard, if not impossible to construct, but you can try in your free time if you're curious. Okay, so in order to explore more patterns in Pascal's triangle, we have to ensure that we have a good understanding of combinatorics. So here we're going to do a quick review for it. So again, combinations are denoted as NCR. I think I skipped a slide. Sorry. Right, so before we go into combinatorics, this is why we have to review combinatorics, because the numbers in Pascal's triangle are actually all binomial coefficients, right? So in other words, these little weird parentheses fractions here are called binomial coefficients. Binomial coefficients. Why they're called binomial coefficients, you will find out very soon. But if you have studied combinations before, you would know that, by the way, binomial coefficients is just another way of saying combinations. And if you studied combinations before, you would know that, for example, 0 choose 0 evaluates to 1. 1 choose 0 evaluates to 1. 1 choose 1 evaluates to 1. 2 choose 0 evaluates to 1. 2 choose 1 evaluates to 2. This is 1. This is 1. This is 3. This is 3. This is 1. This is 1. This is 4. This is 6. This is 4. This is 1. Are you guys noticing a pattern here? This is 5. This is 10. This is 5. No, sorry, that's not 5. This is also 10. This is 5. And this is 1. Do you guys notice a pattern? My mom is speaking pic of the Pascal's triangle.
Think so. Because like 1 2 1, 1 3 3 1, 1 4 6 4, 1 and 1 5 10 10 5 1. So I guess
know.
triangle gets bigger, and then there's also added a middle number, I guess.
I know, it's almost as if these numbers are all over here. Oh my god.
Could there be, I don't know, this one's not, could there be a oh, I don't know.
So this is very interesting because this shows that Pascal's triangle is not simply a random structure you get by adding numbers together. Pascal's triangle is actually deeply related to the study of combinatorics and combinations. And as you can see here, Pascal's triangle is actually composed entirely of combinations. All of these parentheses thingies that are called binomial coefficients are combinations, and they all show up in Pascal's triangle. In fact, they make up Pascal's triangle. Why is the 4 over the 3 becomes 4? Charlotte, we're going to review that real quick. I know that some of you guys aren't really familiar with binomial coefficients, so we're going to do that right now. So a quick review for binomial coefficients. Combinations are denoted as n choose r. This is one way you can denote it, and it's pronounced n choose r. And it is also can be written as the binomial coefficient notation as displayed in the previous slide, which is like the little fraction thingy inside a little parenthesis thingy. That's called the binomial coefficient notation. So the r refers to the number of objects you are choosing, while n refers to the total amount of objects you are choosing from. Recall that we evaluate n choose r using this formula right here. And in case you guys are completely confused by why combinations exist, basically n choose r is the number of ways to choose r volunteers from a classroom of n students. Right, let me write that down in case you guys are not very. So again, n choose r equals n choose r is simply equal to the number of ways to choose r volunteers from a class of n students. So for example, 3 choose 1 would be the number of ways to choose one volunteer from a class of 3 students, which comprises of Lloyd, Joyce, and Asher. And 4 choose 2 would be the number of ways to choose 2 volunteers from a class of 4 students. And again, in combinations, order doesn't matter, which is why we're using the volunteers metaphor. So does combinations make sense for you guys, or should we spend a little more time going over it? Brayden, Charlotte, are you guys masters at combinations, or do you guys want a little more time reviewing it? NCR. Well, Asher, you gave me how many students we're choosing from, but how many students are you choosing? 1,000. Well, Asher, we can't really choose 10,000 students from a classroom of 10 students, right? And the 4 over the 3, which one is the n? Yeah, Charlotte, so let me show you the notation really quick. So again, this is another notation for writing NCR. It really just denotes the same thing. But when you write it like this, the top one is N, the bottom is R. So for choose 3, this one would mean that you're choosing 3 volunteers from a classroom that has 4 students. It's really just a different notation. The top is the number of students you're choosing from. The bottom one is how many you're choosing. 1, 6, 20, 20, 20. Yep, that's the next row. That's right. Okay, let me show you guys how to evaluate combinations. I think that would help you guys understand a lot better. So how you evaluate a combination is really built upon how you evaluate a permutation, right? I think if you guys know a bit basics of permutations, this will make a lot more sense. So let's start out with this example. Suppose that Braden has the entire Harry Potter series in his bookshelf. And for you Harry Potter fans, you know that there's 7 Harry Potter books. And Charlotte is wondering, in how many ways can Braden rearrange all 7 of his books on his bookshelf? Well, there would be 7 factorial ways, right? Because for his first slot, Braden can have 7 choices of choosing which book is the first book, which book is the one to the leftist or the rightist, depending on which direction you want to start from. And then for the second book, Braden actually does have a collection. That's great. For the second book, Braden has 6 choices of which book goes behind the first book. And then for the third book, Braden has 5 choices because he already used up 2 choices. You already used up 2 books. And it keeps on going forever until you multiply it down to 1, right? And it's the same thing if you're choosing like class officers in a classroom. So say that we have a class of 5 people and you want to choose a class president and I don't know, a vice president. So therefore you would have 5 choices of which student is the class president. And then you have 4 choices of choosing which student is the vice president or the treasurer, whatever. Well, we said class president and vice president, right? Yeah. So you have 4 choices for which student is the vice president. So that means you have 20 ways of choosing. But these are all permutations, right? So the order in which you choose them matters. So as we went over a few classes ago, the reason permutations and combinations are different is that while permutation, the choices orders matters, as we have said, class officers, president, and vice president. In a combination, the order doesn't matter. And this is when we use the volunteers metaphor. So now, instead of choosing class officers, we're going to choose 2 volunteers from the classroom of 5 people. So that means we're choosing 2 people, but the order in which we choose them doesn't matter because it's the same position. So if you start with 5 times 4, you're implying that you're choosing 2 different, distinct positions, right? You would be choosing like volunteer officer and assistant volunteer, right? 5 times 4 would be 2 different kind of volunteers. But if we want only a committee of volunteer, which means that everyone chosen is the same, then that means you have to divide that by 2, right? Because it doesn't matter which person is chosen first. And similarly, if you're choosing a volunteer committee of, I don't know, 3 people from a class of 10 students, that means you would be evaluating. We are 5 students in the class right now. That's right. That means you would be first starting out with 10 times 9 times 8. However, this implies that you're considering distinct positions for the volunteers. But again, order doesn't matter. The order in which we choose the volunteers does not matter because they're just volunteers. So that means you have to divide that by 3 factorial. because you have to overcount the number of ways in which you overcounted. So you have to divide by 3 factorial. And notice that when you actually evaluate a combination, it's actually a little bit different than this formula, because in the actual formula you would be computing 10 factorial over 3 factorial times 10 minus 3 equals 7 factorial, right? But the formula in which we wrote down here is actually a little bit different, because when you're computing combinations, you don't have to use this formula. You can just think about it, right? Say that you're computing 9 choose 2. So what I would think is, okay, I'm choosing 2 guys from a class of 9 people to be volunteers. And if I start out with 9 times 8, which would be a permutation for choosing class officers, that's overcounting, because the 2 guys are on the same committee. It doesn't matter which guy is chosen first. So you got to divide by 2 factorial to correct the overcounting. So does this make sense, guys? Is it still confusing? Okay, should be good. Okay, so now here is a really interesting question. So suppose that there is a little cat sitting on 0, 0, 0, choose 0. And so the question is, how many paths are there for this little cat to go from 0, 0 to 3, choose 2? So how many paths are there between these 2 points? I'll let you think about it for a little bit. Remember that the paths can only go down, right, or down left. So it can't go back up like that. So how many paths are there from 0, 0 to 3, 2? Does anyone have any idea? Well, guys, spoiler, the number of paths is actually exactly 3, choose 2. And as a brief review, yep, Braden, it is 3. Yep, exactly. And someone that understands combinations, tell me, what does 3, choose 2 equal to? Like, what does 3, choose 2 evaluate to? What does this binomial coefficient evaluate to? What does this combination evaluate to? Guys, Braden already gave you the answer. 3. Yep. The number of ways to choose 2 volunteers from a class of 3 people is exactly 3. And as Braden already said, the number of paths is coincidentally also 3. That's really interesting. And indeed, we can see that Braden is indeed correct. There's 3 paths. Okay, so apparently the number of paths is exactly equal to the number at the point you're going to. Maybe that's just a coincidence. Why don't we try another example? Say that the cat now wants to go to 4, choose 2. How many paths are there from 0, 0 to 4, choose 2? 10 for, not quite. Not quite, guys. 8, 1, 6. Bingo. It is 6. So first of all, we can maybe like experimentally verify that there is indeed 6. 1, 2, 3, 4, 5, 6. Okay, so yeah, there is 6 paths. And what does 4, choose 2 evaluate to? What does this binomial coefficient evaluate to? Can I have the formula again? Of course. Ashley, that's right. It evaluates to 6. Here's the formula. Here, how about I'll write this on the top for you so that you can keep it. So it would be n factorial over r factorial times n minus r factorial. But again, Charlotte, I would prefer it, and I believe you would also prefer it if you really, understand the meaning behind a combination, which is, the number of ways to choose volunteers from a classroom. But here is the formula. So again, we see that the number of paths is exactly the number that corresponds to this binomial coefficient, which is 6. So that's really interesting. Let's think about why this happens. Because indeed, this happens in general. Like, indeed, if you choose to go to any random point on Pascal's triangle from 0, 0, you would see that there are exactly the number of paths that correspond to the number corresponding to the binomial coefficient. For example, if you want to go to 5, 3, 5 choose 3, then you would have exactly 10 paths to go. If you choose to go to 5 choose 4, you would have exactly 5 paths to go. And the reason this is the case is actually stemming from the grid walking theory, which is, for example, if you consider this grid, right? You want to go from this point to this point. You have to go down right twice, and you have to go down left once. But it doesn't matter which order you choose to go down right and go down left. So that means out of the 3 steps you have to take, 2 of these has to be going right. But it doesn't matter which order you go right. You could go right, left, right, or you could go right, right, left, or you could go left, right, right. So it doesn't matter. So that means the number of paths is simply the number of rearrangements of right, right, left, right? And that's simply just 3 choose 2, which is 3, right? And another example would be if you want to go to 5 choose 2, then you would be considering a grid like this, right? A grid like this. And you would see that you have to go left 3 times and right 2 times, right? But it doesn't matter which order you go left and which order you go right, as long as you go left 3 times and right 2 times. So out of the 5 steps you have to take, 2 of them has to be going right. But so as a result, this is also the number of paths you could possibly take, and that evaluates to 10, as we have seen before. Yep. And so this is a really cool property of Pascal's triangle, counting grids. Okay, finally, applications of Pascal's triangle, the exciting part. So first of all, Pascal's triangle gives us a really cool identity in combinatorics. And this is known as, hint, Pascal's identity. And that identity is written here. So how we get this formula is really from the way in which Pascal's triangle is created, right? Because as you guys must recall, Pascal's triangle is formed by taking 2 adjacent numbers, adding them together, and putting the result on the bottom between them. And check out this formula. That's exactly what it's saying. It's saying that if you take 2 adjacent numbers and add them together, you get the number below them. That's just the Pascal's identity. You know what, guys? Let's try out this formula. Braden, why don't you give me 2 combinations that are next to each other on Pascal's triangle? So give me 2 random numbers like this. Three choose 2 and 5 choose 3. No, Braden, we can't do that because we have to choose 2 binomial coefficients that are next to each other. If someone else went 4 choose 3 and 4 choose 3. Okay, we can do that. Okay. All right. So, Braden, if we evaluated 4 choose 2 plus 4 choose 3, based on the formula, what would the answer be in terms of binomial coefficients? What would the answer be without even evaluating it? Charlotte, I don't think it's 100. Does anyone want to conjecture what the answer would be, adding 4 choose 2 and 4 choose 3 together? Remember that we're just using this formula, guys. Wait a sec. Okay, Asher. Remember, Pascal's identity states that when you add two adjacent numbers in Pascal's triangle together, you get the number below them. So if you add 4 choose 2 and 4 choose 3, you would get the number that's below them, right? It's not 8 choose 5, Brayden. Here, let's look at Pascal's triangle again, shall we? What is below 4 choose 2 and 4 choose 3?
Choose 3.
Yep, indeed. So Pascal's identity would tell us that without even evaluating this stuff, the answer should be 5 choose 3, which would evaluate to 10. Okay, so now let's check this formula. Let's see if it's really correct. Guys, what is 4 choose 2? What does it evaluate to? And someone also tell me, what does 4 choose 3 evaluate to? What does 4 choose 2 and 4 choose 3 evaluate to? What numbers do these binomial coefficients correspond to? Well, guys, let's think about it. Like 124, not quite. Guys, if you have a classroom of 4 people and you want to choose 3 volunteers, how many ways can you do that? If you have 4 total students and you want to choose 3 of them to be volunteers, how many ways can you choose these 3 students? Well, it would be 4, right, guys? Because if you have 4 people, okay, let's think about it like this. We have 4 students: Joyce, Asher, Brayden, and Charlotte, and we want to choose 3 of them to be volunteers. So that means we can either kick Joyce out of the committee, or we could kick Asher out of the committee, or we could kick Brayden out of the committee, or we could kick Charlotte out of the committee. So there's 4 ways to form the committee, right? So 4 choose 3 evaluates to 4. What does 4 choose 2 evaluate to? How many ways are there to choose 2 students from 4 students?
Could you say that again?
What was that?
Could you say that again?
Right, so we are trying to evaluate 4 choose 2, and that is basically the number of ways to choose 2 students from a class of 4 students. So how many ways can you choose 2 per people from 4 people? It's very close. 12 is very close, but maybe you have to divide by 2. Sorry, I have to charge my computer. It's running dead. 6. That's right. If you just think about it, it does make sense, right? Because if you have Joyce, Asher, Brayden, Charlotte, there's 6 ways to choose 2 of you guys. Yep. And if we look at it, guess what? What is 6 plus 10? 6 plus 4 add up to? It adds up to 10. And what does 5 choose 3 evaluate to? 10. Boom. So yeah, that just proves, I mean, not prove, but give you an intuitive demonstration of how Pascal's identity works. This is a very powerful theorem when you're trying to prove stuff in mathematics, and you should keep this identity in mind. And it's really, it's a really simple identity. It just comes from how the Pascal's triangle is constructed. Okay, so now we are going to discuss something that's even cooler, and that is the legendary binomial theorem. So, before we discuss the binomial theorem, let's look at this expansion, right? So, if you're trying to evaluate and expand x plus y squared, you would use your normal rules of distributive property, right? Because x plus y squared is x plus y times x plus y. X times x is xx. X times y is xy plus yx plus yy. And this evaluates to x squared plus 2xy plus y squared. That's easy, Charlotte. That's good. Yep. First, it was Pascal, now it's binomial. Well, Braden, you will see that it's actually deeply connected. And I'm going to show you now very soon. So before we go to the next one, I want you to keep in mind these coefficients. Remember that when there's no number in front of a variable, it just means 1, right? So I want you to keep in mind these coefficients 1, 2, and 1. Maybe we've seen these numbers somewhere. Okay, let's look at another one. X plus y cubed expanded. How would you do that? You would, again, use your normal rules of distributive property and expand this, right? And you just use your distributive property and you would get this.
Wait, is the middle line like xx plus xxy? Is it like combination? Like how much time? Something I don't know.
Asher, I couldn't really hear you a little quiet. Can you say that again?
Like, is the x plus y to the power 3? Like the middle is xx plus xxy plus xyx plus xxy. Is it like how many ways there's to do that thing? Something.
Right. So notice how these are just the terms you get when you expand this binomial, right? So xxx derives from taking x and multiplying them together. Xxy comes from taking x and y and multiplying them together. And then you just like keep on going, right? So for example, yxx is 1y times x times x. And again, I want you to keep in mind these coefficients. Have we seen these numbers somewhere, guys? Do these numbers look familiar? I don't know. Charlotte.
It looks like the triangle. No, I was kidding. I don't know.
Guys, I heard a keyword in Nasser. He said triangle. Oh my God. Remember 121 from the previous expansion? What does this look like, guys?
This looks
Wait.
like the dude's triangle or something.
Yes. Yes. This is Pascal's triangle. These numbers are straight from Pascal's triangle. Because look at Pascal's triangle. 1, 2, 1, 1, 3, 3, 1. It's literally straight out of Pascal's triangle. Okay, so now we are going to figure out why. And indeed, the cool thing about this is that indeed the coefficients of a binomial are exactly just the rows of Pascal's triangle, right? So if you were evaluating, let's say, I don't know, x plus y equals 4 into the fourth, that would simply be the numbers in the fourth row of Pascal's triangle, right? So it would simply just be x to the fourth power times 4x to the cube times y times 6 plus 6 x squared y squared plus 4 xy to the cube plus 1. And notice that these coefficients are straight out of Pascal's triangle, right? You see these numbers? It's 1, 4, 6, 4, 1, straight out of Pascal's triangle. So that means with Pascal's triangle, you can expand x plus y to any power, and you can literally just copy down the coefficients one by one, and you have already expanded it. Okay, so Charlotte wonders why this works. So now we're going to figure that out. Why does this work? And indeed, this is what we just did. Look carefully, are these coefficients familiar? They are familiar because they are from Pascal's triangle. 1, 2, 1, 1, 3, 3, 1. Okay, so before we explore why this works, we will demonstrate that what we just noticed is the work of the binomial theorem. And that simply states for any positive integer n, the coefficient of the x to the n minus k times y to the k term of x plus y to the nth power is n choose k. In other words, x plus y to the nth power is this. So in other words, if you were evaluating x plus y to, I don't know, the fifth power, then you would simply get 5 choose 0 times x to the fifth plus 5 choose 1 times x to the fourth y plus all the way to 5 choose 5 times y to the fifth. So in other words, you can instantly expand binomials that are raised to powers that are too big to compute normally, and you can just evaluate it instantly using the binomial theorem. So now we're going to demonstrate why it works. So indeed, this actually makes a lot of sense because, again, guys, remember, what is a combination? Right? What is a combination? A combination is just the number of ways to choose R objects from a total of n objects, right? So that means when you're multiplying and expanding x plus y to the n together, you're simply multiplying n copies of x plus y together, right? Like you're simply multiplying n of these together. And to form each term, you pick a number of x's and a number of y's out of a total of n factors. This is simply combinatorics. It's just combinations. So that means when we choose k copies of x and choose the remaining copies of y, the coefficient of this particular term would be nck, right? So can you guys come up with some examples? So for example, what would be the coefficient? Let's say, okay, so let's say that we are evaluating x plus y to the seventh power. So what would the coefficient of x4, y3 be? What's the coefficient? What's the number that would go in front of this? Seven. Ha, not quite, but it's a good guess. Guys, the formula is like we just saw it. It's just combinations. 12. Not quite. Wait. Would it be helpful that I show you guys the binomial theorem again? Seven x. Not. I mean, no, not quite. Sorry. Guys, notice how in the binomial theorem, notice how the coefficient of the term with a power of y that's k is simply n choose k. right? There's a pattern here because the coefficient of xn minus k, yk is n choose k, right? Brandon goes, whoa, can I use a calculator? Sure. So while Charlotte uses her calculator, we would see that isn't the coefficient of x to the fourth y3 just 7 choose 3, right? Because you have what? You have 7 copies of xy, 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 this stuff multiplied together, right? You have 7 of these, and you're choosing from 3 of these a y term, and the remaining terms you choose an x. So that means you're choosing 3 objects from 7 objects, right? So that means the number of terms, or I guess the number of copies of this is 7 choose 3, which means that the coefficient would be 7 choose 3. Charlotte, did you evaluate this with your calculator? Not yet. Well, I'll evaluate it for you. This would end up to be 35. 7 choose 3 is equal to 7 times 6 times 5 divided by 3 factorial, which is equal to 7 times 5, which is 35. So the coefficient would be 35 x to the fourth times y to the third. All right, okay, guys, I have one final cool thing to show you guys. So there is one final pattern in Pascal's triangle. So if you look horizontally and add the numbers up, you would notice that they seem to be powers of 2, right? For example, the first row, I mean the 0th row adds up to 1. The first row adds up to 2. Second row adds up to 4. Third row adds up to 8. Next row is 512. Yep. And then you have 1024 and then 2048. Right, exactly. So indeed, each row of Pascal's triangle just adds up to a power of 2. So now let's consider why this happens. Why? It's simple. It's just a binomial theorem. Because if we let both x and y equal 1, the formula just becomes 1 plus 1 to the nth equals 2 to the nth equals n choose 0 plus n choose 1 plus n choose n. And again, guys, this is just the binomial coefficients in a row of Pascal's triangle, right? So that means each row of Pascal's triangle adds up to 2 raised up to that row's number, right? So now let's revisit that previous slide again. So since this row is row 0, it is equal to 2 to the 0th power. Since this row is row 1, it is equal to 2 to the first power. And similarly, oh my God, my bad. Since this row is equal to the second row, this is equal to 2 to the second power. This is 2 to the third power. This is 2 to the fifth power. It corresponds, and it's really interesting. So soon there will be that big number, which is 2 to the power of 29. Exactly, Braden. And it will happen at exactly the 29th row of Pascal's triangle. All right, we covered a lot in this class. Do you guys have any questions?
Why did the guy created it?
Sorry, Asher, what was that?
Why did the guy created it?
Well, because, well, I think most likely he first came up with this triangle while he was just experimenting, right? You know, like he was just like drawing random numbers, and he was like, okay, why don't I draw a triangular pyramid that has like numbers adding up to each other? So he made this little weird configuration, and he realized, oh my God, this has so many applications to mathematics, and in particular, it has so many applications to combinatorics. So therefore, this weird structure became widely used among mathematicians, and it was used to derive many important identities that are crucial to the study of combinatorics.
I bet he got famous.
Was it to solve the secrets of triangles? Braden, maybe. Mathematics is all intercorrelated. So one part of mathematics is always related to another.
I think using the pencil triangle, you can find any number, but then it'll be very long. Like if you're doing for 1 mil.
Yep, actually, that's right. Again, as we have talked about, you can find any positive integer that you want in Pascal's triangle, right? Counting numbers. Every counting number is in Pascal's triangle. All right, we covered a lot, and we have unfortunately reached the end of our class. So if you have any questions, feel free to stay, but if not, thank you so much for coming.
Excuse me, algebra is important for stuff. We can say
No.
that A equals 3, something. I don't know. Bye bye. Thank you.
Bye.